So in this video, we will be having a look at the symmetric and antisymmetric FIR filters. So I had explained to you, let me just go through once again, what is the basic requirement for your filter to be stable, or for your FIR filter is supposed to have linear phase. If you want a linear phase FIR filter, this is what we desire to have. So there are two things. Firstly, your h of n, or your impulse response, should have a finite duration, and the next thing is your h of n should be either symmetric or antisymmetric. Even when we design the filter, in order to ensure that the filter is either symmetric or antisymmetric, basically we will substitute your phase value, whatever phase value we have, alpha, we'll be seeing later. Okay, we adjust the alpha value such that the alpha and capital N, the order of the filter and everything is in such a way that it is going to have a linear phase. So we want to understand what is this symmetric and antisymmetric filters, and what exactly is the expression we are going to obtain for symmetric and antisymmetric FIR filters. How is the impulse response going to be in the frequency domain? We get an expression, and here, depending upon the value of capital N, the order of the filter, the capital N value, okay, or the length of the filter, this capital N, if it is even, what happens? If it is odd, what happens? Suppose your capital N is even, okay, if it is an even filter, say for example, let me take the number 6. So when I take the number 6, the value of small n varies from 0 to capital N minus 1, that is 0 to 5 it varies. Okay, sixth value is not there. So if it is symmetric, if the impulse response is symmetric, it is going to be look something like this. That is exactly at the center. 0 to 5 means the midpoint is 2.5. That is, you can write it as 0 n minus 1 by 2. Capital N is 6. So you can write the midpoint as n minus 1 by 2, which is 2.5 in this case. Okay. The sample 2 you can denote as n by 2 minus 1. This is 6 by 2 minus 1. That is 2. And you can write this sample as n by 2. That is your 3. Value 3 you can write as n by 2. So this is how you represent an n even and symmetric filter. So about the midpoint, you can see the samples. Sample at index 2 and index 3 are similar, symmetric, same. Sample at 1 and sample at 4 is symmetric. So this is how a symmetric filter with n equal to even will look. So this is, in general, you can write it like this. For capital N even, these are the index values. So for capital N odd, also it is the same. Only thing is, if capital N is odd, the values will vary from 0 to n minus 1 again. Suppose it is 7. Then what is the mid value here? The values vary from 0 to 6. So 0 to 6 means midpoint of the 6 is 3. So I can write the midpoint value again as n minus 1 by 2. Isn't it? I can write it as n minus 1 by 2. Sample 2, how do I express? I can write it as 7 minus 3 by 2 is 2. So I can write it as capital N minus 3 by 2. How do I write 4? I can write it as n plus 1, that is 7 plus 1 by 2, right? This is how I can express it. Okay. So in case of n odd, you will have, even at the midpoint, you will have one sample, and it is symmetric across both the sides, across the left side and right side. You can see that the values are symmetric. Whatever is the amplitude of the value at 2, the same amplitude holds good at value at 4. That means at the sample in general, at n minus 3 by 2, whatever sample you have, and n plus 1 by 2, whatever you have, is the same. So how can you write 5? You can write it as n plus 3 by 2. Okay, n plus 1 by 2, n plus 3 by 2. Okay, and so on. Here you can write it as n minus 3 by 2, this one. How can you write 1? You can write it as n minus 4 by 2. Okay, sorry, n minus 5 by 2. That is 7 minus 5 is 2, 2 by 2 is 1, okay, 3, 5 and so on, okay. So center value is n minus 1 by 2, n minus 3 by 2, n minus 5 by 2 and so on. This will be n plus 1 by 2, n plus 3 by 2 and so on. You're interested only in these values. This is just to establish the symmetric values, okay. For n equal to odd, this is how the symmetry looks, your h of n value. So all this is nothing but your h of n values, okay. This is h of n. This is also your h of n. This is for n even, n odd. How about, in general you can write it this way, n odd, okay, n minus 1 by 2, n minus 3 by 2, n plus 1 by 2 and so on are the index values. This is your h of n. This is all for symmetric. For antisymmetry now. For antisymmetry, the condition is h of n is equal to minus h of n minus 1 minus n. Okay, this condition is satisfied. So here again, if it is antisymmetric, only thing is, again the midpoint, suppose you take n equal to 6. Midpoint is n minus 1 by 2 is the same, n by 2 minus 1 and n by 2. All this remains the same. Only thing is, it will have opposite signs in terms of magnitude. Magnitude will remain the same, but the sign will be different. So this is how the antisymmetric filter looks for n even, n odd. The index values again remain the same. So in order to find the impulse response of the filter in terms of, in exploiting the symmetric nature and everything, we will look at the Z transform of that. So let us write, suppose we consider the Z transform of a causal finite duration sequence h of n, okay. Causal means here we say that we are beginning at, say, n equal to 0, okay, to capital N minus 1. So this is the length of the impulse response we are going to restrict. Of course, in the next future we will see that we will be doing this using windows, okay. Using windows we will restrict the length of the infinitely long impulse response, but we want to have a finite duration h of n for linear phase FIR filter, and it has to be either symmetric or antisymmetric. So looking at the symmetry and antisymmetry, in order to say that it is symmetric or antisymmetric, this is what we will make use of. Let us make use of the Z transform, which will help us to establish a relationship perfectly. So h of z is given by h of n z power minus n summation over n equal to 0 to n minus 1. For a causal sequence, you know this is the Z transform. Now, let us refer to figure 1. Let us call it as figure 1, wherein for n equal to, n is even, capital N being even, we will split this summation. Okay, so please have a look at n is equal to even. So for n is even and the symmetric condition, okay. Now first we are going to consider the n even and the symmetric case. We are going to consider that it is going to be symmetric. Okay, so n even and symmetric means this is your figure 1, the first figure. Summation can be broken down from 0 to n by 2 minus 1. See, at exact center you don't have the sample, right, at n by 2. That is, we had taken an example n equal to 6 and I had explained to you. So you see here, n equal to 6 means 0 to 5. That is at 2.5 n minus 1 by 2. 2.5 don't have any samples. So you are going to vary the summation from 0 to 2 and 3 to 5. So it's, if you just take this half, it is as good as taking the next half in the reverse order, right? So that is what we are going to establish. So our summation can be broken down from 0 to n by 2 minus 1. Okay, that is still this sample. At the center, you don't have, at n minus 1 by 2, you don't have anything. That is, it is symmetric about this point, right? Next summation can be taken from n by 2 to n minus 1. So that is what we will split our summation right now. 0 to n minus 1, we are going to write it as h of z is equal to summation n equal to 0 to n by 2 minus 1 h of n z power minus n plus summation n equal to n by 2 to n minus 1 h of n z power minus n. I hope this is very well understood. 0 to n by 2 minus 1, across the center there is no value, n by 2 to n minus 1. You have split this summation in this form. Okay. Alright, what to do next? Let us assume some dummy variable. Okay, let us assume some dummy variable. Let some m is equal to n minus 1 minus n. So since we are taking the symmetric case, since this is symmetric case, we know that in the bracket, you know, h of n has to be equal to h of n minus 1 minus n, isn't it? This is the case for symmetric. Now you have taken the condition, your capital N, the filter's length, the length, finite duration till which you are considering your value. That capital N is even and it is symmetric. So you split the summation in this way. Let sum m is equal to n minus 1 minus n. Okay. So I can say that this second summation value, this index is nothing but that n minus 1 minus n, right? Are you getting it? So what happens? If we put some m is equal to n minus 1 minus n, what is going to happen? Here it is as good as writing, if m is given like this, you can write your small n as n minus 1 minus m. So this we will substitute in the second summation because we know that it is having a symmetric nature across the center, right? It is having a symmetric nature across the center. So this portion you can say this is h of n. This is your h of n minus 1 minus n. See, that was the condition we had, right? The condition, this one for symmetric condition, n minus 1 minus n. Okay. So that is what we are doing. So we substitute this value n minus 1 minus m in the second summation. So we will see what happens to the summation when n is equal to n by 2. Okay, when n is equal to n by 2, what is the value of m? M is equal to, see here, when n is equal to n by 2, you can substitute and tell me. M is equal to n minus 1 minus n by 2. So n minus n by 2 is nothing but n by 2 minus 1. Okay. And when n is equal to n minus 1, the second limit is n by 2 and n minus 1. What happens to m? M is equal to n minus 1 minus of n minus 1, which is nothing but 0. So your new limits are what? M is equal to n by 2 minus 1 and m is equal to 0. These are the new limits which you are going to substitute in this equation. You give some number to this. So you call this as equation 1. So substituting the limits in equation 1. What do we get? We get h of z is equal to summation n equal to 0 to n by 2 minus 1 h of n z bar minus n plus summation, now this is m is equal to, m varies from n by 2 minus 1 to 0 h of n minus 1 minus m z bar minus n minus 1 minus m. Got it? So we replaced m with n minus 1 minus n. Okay, this is what we did. So your n becomes n minus 1 minus m, which we substituted here. And the limits, what happened to the limits? We calculated and accordingly we changed these limits. Why we are doing this replacing is like this, so that we can, if the filter is symmetric, we'll see what is going to happen. Okay, here again your m is a dummy variable. It can be replaced by n. Okay, whether you write m or n, it is the same in this equation. At the same time, you also swap this. Instead of writing n by 2 minus 1 to 0, you write 0 to n by 2 minus 1. Okay, so I will rewrite this equation, rewriting that equation. So if you see your equation, okay, this is what is your equation you will get. Since m is a dummy variable in this equation, I have named it as equation 2. Since m is a dummy variable here, this m is replaced with n, and the summation is also changed from 0 to n by 2 minus 1, and m is replaced with n, and you rewrite this equation like this. Alright, so now since we are considering the symmetric case, okay, since h of n is equal to h of n minus 1 minus n, as we are considering symmetric case, as we are considering the symmetric case, what can we do? In this equation, I can replace h of n minus 1 minus n by h of n, but the z power will remain, right? You cannot replace your z power value. So your h of z becomes summation n equal to 0 to n by 2 minus 1. You can see now when you change the limits, both the values of the powers of the summation are the same. So common summation I can write, and I can write h of n, and this is same, or you want to rewrite it again, no problem. I can write one more step, n by 2 minus 1, this is h of n, z power minus of n minus 1 minus n. So you can see summation and h of n is same, only this term is different, right? So I can write it like this, h of z is equal to summation n equal to 0 to n by 2 minus 1 h of n into z power minus n plus z power minus of n minus 1 minus n. Okay. Now if you want the frequency response, okay, the frequency response of the digital filter is obtained how? We need everything in terms of omega, right? So the frequency response of the digital filter you will get by substituting z is equal to e power j omega, which is as good as saying it is h of omega, or when you replace z with e power j omega, it is as good as saying it is h of e power j omega or h of omega, it is the same. So I can write it, okay, so h of e power j omega is equal to, you can also say it is h of omega. This is nothing but your frequency response. So here I have told you, you will have both the magnitude response and the phase response. So I am going to write this. See, the beauty of this equation is that you're getting the frequency term, and just by taking the time domain impulse response, you're able to obtain this. So it is very easy for you to do the calculations if you remember. So we will get h of n into e power minus j omega n plus e power minus j omega, because you're replacing z, this is replaced, and n minus 1 minus n remains. So in the next step it is, so we have the range this way. We will do a little bit of rearrangement here so that we can write it in terms of sine and cos. So what I'll do is, I will write it like this: n equal to 0 to n by 2 minus 1, 2 into h of n. I'll multiply and divide by 2 because I want it in terms of cos or sine, whatever is obtained. So since plus sign is there, I will try to write it in terms of cos. Okay, so I'll multiply and divide by 2, and I will remove common here. Okay, 2 h of n e power minus j omega n minus 1 by 2. We know here n minus 1 by 2, you can see here n minus 1 by 2 is the center value. So we try to remove this n minus 1 by 2 and try to write it in such a way that you obtain the cosine term or sine term, whatever it is, in terms of this, in order to establish or show the symmetry or write it in a much easier way. So I'll take out here 2 into h of n e power minus j omega into n minus 1 by 2. Okay, and whatever is left inside the bracket, so I'll be left with e power minus j omega into n minus 1 by 2. Okay, because I took out one n minus 1 by 2 out, capital N minus 1 by 2 outside. Okay, this is what will be left, plus e power minus j omega. This is nothing but n minus, this will be e power plus j, because I took out minus j out, n minus 1 by 2. So this whole thing divided by 2. So this simplification, what I have done, how I have taken this is, multiply and divide by 2. This is in order to establish either cosine or sine term. And it's a point to always remove out n minus 1 by 2 here. Okay, when we remove this component out of this, okay, this is how you get it. If you want, I will show you the further simplification of this. So what I will do is, let me just take this term and remove. In order to remove this, how to do it, I will just show you. Okay, so just a moment. So I am going to illustrate this step. I will illustrate this, basically how this has come, how I have removed it common. If you actually do it, you will get it. Okay, but let me do it. So let us consider this equation. I will rewrite it. That is summation, you're considering your h of omega is equal to summation n equal to 0 to n by 2 minus 1 h of n e power minus j omega n plus e power minus j omega n minus 1 minus n. When you take this, you multiplied and divided by 2. Okay, this is in order to obtain this in the form of to write this term in terms of cos or sine. So now what I am going to do, this term, let me show you this term, what happens to this term. So I want to write this in such a way that this exponential will, I want to remove e power minus j omega capital N minus 1 by 2 because that is the midpoint. So let me remove that out. So consider only this term, e power minus j omega n plus e power minus j omega n minus 1 minus n. Okay, I am just considering only this term and I am going to simplify that. So what am I going to do to that? I write this as e power minus j omega small n plus capital N minus 1 by 2 minus capital N minus 1 by 2. Okay, plus e power minus j omega, you have n minus 1. I'll split this n minus 1 as n minus 1 by 2 plus n minus 1 by 2 minus n. So you got the powers, right? These are the powered values. So let me rewrite this. I can rewrite it as e power minus j omega into n into e power minus j omega n minus 1 by 2 into e power plus j omega, this minus and this plus, minus becomes plus, e power plus j omega n minus 1 by 2 plus, I'll open this also, e power plus j omega n minus 1 by 2 e power, sorry, this is minus, e power minus j omega into this, again e power minus j omega n minus 1 by 2 into e power j omega n. Okay, is it okay? Minus j omega n minus 1 by 2 minus 1 by 2 e power minus j omega minus into minus plus jn. Okay, these are the terms. So I have here I have added and subtracted n minus 1 by 2. Here whatever n minus 1 is there, I split it as n minus 1 by 2 plus 1 n minus 1 by 2 and wrote it this way. So what is my goal? I want e power minus j omega n minus 1 by 2 because I want the phase angle term, negative phase angle term outside. That is the reason I am writing it like this. Okay, the same way you will do it for everything. So remember, it is just this term that I am simplifying here. So what happens to this? This becomes e power minus j omega n minus 1 by 2 I removed out. So I am left with e power minus j omega n into e power j omega n minus 1 by 2 plus e power minus j omega n minus 1 by 2 into e power j omega n. Okay, power j omega n, e power 1 of the minus j omega n minus 1 by 2 term, and here e power minus j omega n minus 1 by 2 is out, this and this term. So what are the terms that are inside the bracket? This is inside. In this case it is this term and this term. 1 e power minus j omega, I have removed it common. This is that common term. Okay, I hope you have understood this. So now simplify the term inside. E power minus j omega n minus 1 by 2. Okay, what happens to this term? This is e power, you remove minus j omega out because you want n value. Always try to keep the small n value positive, sign positive inside. So this is n. You have removed minus out, so this becomes minus n minus 1 by 2. Okay, this is plus e power, already the power of n is positive, so remove only e power j omega out, plus, so n minus is already there, n minus 1 by 2. This is the term you got. This is how you got it. So this is only the simplification of whatever you have got simplified here. You can substitute instead of this. So therefore your h of omega is summation n equal to 0 to n by 2 minus 1, 2 times h of n e power minus j omega n minus 1 by 2, this term, into e power minus j omega n minus 1 by 2 plus e power plus j omega n minus 1 by 2 whole thing by 2. Hope you have got this. This is what we had done here. This is what we had got, this step. I've just illustrated how we got that step. So this h of omega is of the form hr of omega, the magnitude term and the phase term, e power j theta of omega. Okay, so hr of omega is equal to, you can write the real term. What is this? Okay, you need to write this in terms of cos. Okay, so 0 to n by 2 minus 1, 2 times h of n e power minus j omega n minus 1 by 2. This term e power j theta plus e power minus j theta by 2 is nothing but cos of omega of n minus 1 by 2. In terms of theta, you have this value, right? So this is your expression. Compare these two. So this is not hr, this is h of omega. H of omega is of this form. These two you can compare these two and write down your equation. hr of omega will be what? So hr of omega you compare here, e power j theta is this, hr of omega the rest of the terms. This is nothing but hr of omega, 2 times h of n cos of omega into n minus 1 by 2 summation small n varies from 0 to n by 2 minus 1. So this is your hr of omega. What is the value of theta here? What is the value of theta? E power j theta of omega. Theta of omega is nothing but minus omega n minus 1 by 2. For this value greater than 0, for less than 0 you have to always add pi. This I had told you earlier. So this is your hr of omega. So let me write the value of theta of omega. Minus omega of n minus 1 by 2 for if hr of omega is greater than 0, minus omega of n minus 1 by 2 plus pi if hr of omega is less than 0. So this is for n even. N even. This is your magnitude value. This is your phase value. This is what you have proved for n even. Remember. Okay, right in the starting itself I had told we are doing this for n even. Right. Referring to the first figure, n even, symmetric, we considered all these things. Same thing we can refer to your figure 2. You can consider this as your figure 2. For n odd also we can try to prove the same thing. Only the range of values you will take is from 0 to n minus 3 by 2, the first summation. Second summation from n plus 1 by 2 to n minus 1, and you have an extra sample at n minus 1 by 2. We can do that. So the h of z for n odd and symmetric values vary from 0 to, just write the limits range first, 0 to n minus 3 by 2 you have, then at n minus 1 by 2 you have the center sample, then from n plus 1 by 2 to n minus 1 you have the next set of samples. Okay, so this is the range. So how can I write the h of z? You know, h of z is given by what? Summation n is equal to 0 to n minus 1 h of n z bar minus n. So what do we do? Just like we did here for n even, we split the summation 0 to n by 2 minus 1 to n by 2 to n minus 1 because it is symmetric n even. For symmetric n odd, we know it is from 0 to n minus 3 by 2, n minus 1 by 2, n plus 1 by 2 to n minus 1. So we will split the summation accordingly. So your h of z becomes equal to what? Right here, h of z is equal to summation n varying from 0 to n minus 3 by 2 is the first summation, h of n z bar minus n plus summation n varying from okay, let me write this term, or all right, this center term, we cancel this, h of n minus 1 by 2 plus third term n equal to n plus 1 by 2 to n minus 1 h of n z bar minus n. Okay, this term is not there. Okay, these are the terms that we have. All right, 0 to n minus 3 by 2, middle term n minus 1, because n is odd, you have one value at the center exactly, then n plus 1 by 2 to n minus 1, you have these. Then in case of antisymmetry, we know that our h of n should be equal to minus h of n minus 1 minus n. Alright, so for n even, we know the limits are varying from the same like your symmetry equation. If you look, limit varies from 0 to n by 2 minus 1, and the summation is from n by 2 minus 1 to 0. So for the second term, I have taken n minus 1 minus m z bar minus n minus 1 minus m. This is same as what we have done for your symmetry. Recall, for your symmetric property, n even, we had it this way, right? And because this is the condition, we had substituted, everything remains the same. Whatever we did remains the same. Okay, only thing is we are going to replace your m with n. Whatever steps we have followed earlier, we're doing the same thing. Only thing is we are going to substitute h of n is equal to minus h of n minus 1 minus n. So when we do that, what happens to this term? This becomes minus of h of n, and we get a negative term here. So once we get this is the key difference between symmetry and antisymmetry. Once we are doing this, what happens? This is what we get. Alright, so we take the negative sign, h of n, z bar minus n and all that, and now we want to substitute as usual e power j omega to get the omega frequency. So once we do that, this is what we get. Okay, so we substitute all these values, we write multiply and divide 2j, because negative sign is there, you know, ultimately you want it in terms of sign. Multiply and divide 2j and solve the equation. Remove e power minus j omega n minus 1 by 2 out. So you will be left with one positive term and one negative term of this. And remove this outside and write this in terms of sign. After writing that in terms of sign, the important thing is j, you will replace it as e power j pi by 2. Okay, and this is what you get. So if you look at the term, you have pi by 2 minus j omega. So your angle, earlier it was minus omega n minus 1 by 2. Now your phase angle is pi by 2 minus this angle for your antisymmetry. Okay, pi by 2 minus, that means for the rest of the terms you will get the, in order to account for this whatever change in the phase, you have this negative sign. In terms of phase, it is pi by 2 minus omega into n minus 1 by 2. So if you write it h of omega in terms of e power j omega theta, theta and the magnitude, this is your magnitude, this is your h of n. Okay, so similarly for, this is your magnitude and this is your phase, you can write down the magnitude separately, you can write down the phase separately. Okay, similarly for n antisymmetric, n odd and antisymmetric, what happens at the center, the values get, that is at n minus 1 by 2, you will have two samples of equal and opposite magnitude because of your condition h of n is equal to minus h of n minus 1 minus n. Okay, because of this condition you're going to have it this way. So what happens, these get cancelled and at the center h of n minus 1 by 2 is 0, whereas for n odd and symmetric, what happens, you have this term here, you have one value h of n minus 1 by 2 in your answer. So that is a key difference. So as usual, you substitute the limits from 0 to n minus 3 by 2. This term also you write it, last you can write it as 0, h of n minus 1 by 2, which is 0, and n plus 1 by 2 to n minus 1. Okay, so you substitute, change the limits in such a fashion, replace m with n. Okay, and accordingly you change your limits of summation of this third term. Okay, and you try to obtain changing the limits and rewriting. This is what you get. Then you get this, you substitute your condition, that is n minus 1 equal to minus h of n in the third term. So all the limits will be changed to 0 to n minus 3 by 2. Then you will be getting this equations. So even here multiply and divide by 2j because you have minus term. So you will get your sign term outside. This is what, after simplification, this is what you will be getting. So even here, just like the previous case, you will get h of n sign term. For omega less than 0, you add a pi. So pi plus pi by 2 is 3 pi by 2. This is what you will be getting. Theta of omega. HR of omega is this. So if you actually summarize everything, this is what we'll be getting. For symmetric and even, you have cosine terms. For HR of omega, theta of omega is this. Symmetric odd terms, it is like this. So one thing that you need to remember is, you will always write your h of omega as HR of omega into theta of omega. It will always be in this form. Okay. So this is what you will be getting.